but he's a really incredibly feeble, tiny force.
It would be an uphill battle for Einstein to unify these two forces of wildly different strengths. And to make matters worse, barely had he begun before sweeping changes in the world of physics would leave him behind.
Einstein had achieved so much in the years up to about 1920 that he naturally expected that he could go on by playing the same theoretical games and go on achieving great things. And he couldn't. Nature revealed itself in other ways in the 1920s and 1930s. And the particular tricks and tools that Einstein had at his disposal that had been so fabulously successful just weren't applicable anymore.
You see, in the 1920s, a group of young scientists stole the spotlight from Einstein when they came up with an outlandish new way of thinking about physics. Their vision of the universe was so strange, it makes science fiction look tame, and it turned Einstein's quest for unification on its head.
Unification. Unification.
Led by Danish physicist Niels Bohr, these scientists were uncovering an entirely new realm of the universe. Atoms, long thought to be the smallest constituents of nature, were found to consist of even smaller particles, the now familiar nucleus of protons and neutrons, orbited by electrons. And the theories of Einstein and Maxwell were useless at explaining the bizarre way these tiny bits of matter interact with each other inside the atom.
There was a tremendous mystery about how to account for all this, how to account for what was happening to the nucleus as the atom began to be pried apart in different ways. And the old theories were totally inadequate to the task of explaining them. Gravity was irrelevant, it was far too weak, and electricity and magnetism was not sufficient.
Without a theory to explain this strange new world, these scientists were lost in an unfamiliar atomic territory, looking for any recognizable landmarks.
Then, in the late 1920s, all that changed.
During those years, physicists developed a new theory called quantum mechanics, and it was able to describe the microscopic realm with great success. But here's the thing. Quantum mechanics was so radical a theory that it completely shattered all previous ways of looking at the universe.
Einstein's theories demand that the universe is orderly and predictable. But Niels Bohr disagreed. He and his colleagues proclaimed that at the scale of atoms and particles, the world is a game of chance. At the atomic or quantum level, uncertainty rules. The best you can do, according to quantum mechanics, is predict the chance or probability of one outcome or another. And this strange idea opened the door to an unsettling new picture of reality. It was so unsettling that if the bizarre features of quantum mechanics were noticeable in our everyday world, like they are here in the Quantum Cafe, you might think you'd lost your mind.
The laws in the quantum world are very different from the laws that we are used to. Our daily experiences are totally different from anything that you would see in the quantum world. The quantum world is crazy. It's probably the best way to put it. It's a crazy world.
For nearly 80 years, quantum mechanics has successfully claimed that the strange and bizarre are typical of how our universe actually behaves on extremely small scales.
At the scale of everyday life, we don't directly experience the weirdness of quantum mechanics.
But here, in the Quantum Cafe, big, everyday things sometimes behave as if they were microscopically tiny. And no matter how many times I come here, I never seem to get used to it. I'll have an orange juice, please.
I'll try.
I'll try, she says.
You see, they're not used to people placing definite orders here in the Quantum Cafe because here, everything is ruled by chance. While I'd like an orange juice, there's only a particular probability that I'll actually get one.
And there's no reason to be disappointed with one particular outcome or another because quantum mechanics suggests that each of the possibilities, like getting a yellow juice or a red juice, may actually happen. They just happen to happen in universes that are parallel to ours, universes that seem as real to their inhabitants as our universe seems to us.
If there are 1,000 possibilities and quantum mechanics cannot with certainty say which of the 1,000 it will be, then all 1,000 will happen. Yeah, you can laugh at it and say, well, that has to be wrong. But there are so many other things in physics which at the time that people came up with had to be wrong, but it wasn't. You have to be a little careful, I think, before you say this is clearly wrong.
And even in our own universe, quantum mechanics says there's a chance that things we'd ordinarily think of as impossible can actually happen. For example, there's a chance that particles can pass right through walls or barriers that seem impenetrable to you or me.
There's even a chance that I could pass through something solid, like a wall. Now, quantum calculations do show that the probability for this to happen in the everyday world is so small that I'd need to continue walking into the wall for nearly an eternity before having a reasonable chance of succeeding. But here, these kind of things happen all the time.
You have to learn to abandon those assumptions that you have about the world in order to understand quantum mechanics. In my gut, in my belly, do I feel like I have a deep intuitive understanding of quantum mechanics? No.
And neither did Einstein. He never lost faith that the universe behaves in a certain and predictable way. The idea that all we can do is calculate the odds that things will turn out one way or another was something Einstein deeply resisted.
Quantum mechanics says that you can't know for certain the outcome of any experiment. You can only assign a certain probability to the outcome of any experiment. And this Einstein disliked intensely. He used to say, God does not throw dice.
Yet experiment after experiment showed Einstein was wrong, and that quantum mechanics really does describe how the world works at the subatomic level.
So quantum mechanics is not a luxury, something that you can do without. I mean, why is water the way it is? Why does light go straight through water? Why is it transparent? Why are other things not transparent? How do molecules form? Why are they reacting the way they react?